All right, good morning, students. So today you're really digging into differential equations, and it's going to be, I think, more interesting of a lesson here. If it's too much, please let me know, and we can roll forward some of it to Friday. We have some of the basics of differential equations, like a slope field and what it means to be a solution, as well as our separable differential equations, which are the first and probably the easiest type to solve analytically. And so in this video, I just wanted to really briefly make some comments about each of the different types of things there. So the first activity, slope fields, that's basically visualizing what a differential equation is. And it's a really great visual opportunity to understand it. So basically the idea of a slope field is, let's say we have a differential equation like dy dx equals x plus y. What that means is that the slope at any given point is equal to the x coordinate plus the y coordinate. And so if you're trying to create your slope field, I know that the slope at 0, 0 is going to be 0 plus 0. I know the slope at 1 comma 0 is going to be 1 plus 0. So that's my attempt at a slope of 1. Then here's like a slope of 2, slope of 3. And so as I move further to the right, they get progressively steeper. For the exact same logic, as I move up, they get progressively steeper. As I move up and to the right, I have more and more steep little tick marks. So each of these represents the slope of the solution at that point. As I look at a point like, for example, this one of negative 1 comma 1, negative 1 plus 1 is 0. So I have here a slope of 0. Negative 2 plus 2 is 0. Negative 3 plus 3 is 0. Along this line, going down at a 45-degree angle, because the x and the y are opposites, we have slopes of 0. And you can calculate any slope by doing this same way. As I go to the left, I have negative slopes that get progressively steeper, negative slopes that get progressively steeper, etc. And what you can do is choose an initial condition, and then you just kind of ride the slope field as you go. So I'm going to use a different color so you can see what I'm doing here. Let's just say I start here. This is my initial condition. Well, if I'm there, my slope is 0, so I go to the right. And then my slope is 1, so I go up. Then my slope is steeper, so I go up. So it's going to create some sort of a curve like that. Then you can also extend your logic to the left, and as I move to the left in a flat direction, I reach a negative slope. It's going to be doing something like this as we go to the left. It becomes really a pain in the butt to draw it perfectly, but the point of a slope field is that you start to get a general feel for how the solution curve looks. So that's your first activity. Second activity is talking about solutions to differential equations. And so if you have a given differential equation and you want to check if it is a solution, that's when you plug in, just like if you had an equation, you'd plug in the x values to check that it worked. Here you're going to be plugging in an entire function to see if it is the solution to a differential equation. So for example, this is sort of a silly example, but if I had dy dx is equal to 3y, and I wanted to check a solution here, I'm claiming that if I have y equals e to the 3x plus 4, here, let me get rid of them, then what I can do is, let's delete the plus 4. If I have y equals e to the 3x, what I can do is substitute that back in. So I substitute that here on the left side, and I also have to calculate dy dx, which by the chain rule is e to the 3x times 3. And so what I end up with is dy dx, e to the 3x times 3. Does that, you're plugging it in, does that equal 3 times y, and it turns out to be true. And so just think about it like when you're solving an equation, you get a solution, and then you plug it back in to make sure it worked. And so when you're doing this second activity about solutions to differential equations, you're going to be plugging things in. And when you plug it in, uh, you're going to often have to plug in the derivative as well. You're going to have to plug in the derivative as well to make sure that it works. All right, so then next up, I'll do the last two all as one here, writing differential equations and separable differential equations. So this is taking a situation and modeling it with a differential equation. And one example that makes a lot of sense right now is when you think about the population growth, and you can think of it as a virus or any other living thing. But typically, what happens is if you have a population, we can call it dy dx. So that's the change in the population over time. And a lot of times, what happens is it's proportional to the current population. And so if you see that word proportional, typically we'll use a constant. We use the letter k here because we use the plus c when we take the integral. So we'll just use the letter k for constant. And so if the rate of change of the population is proportional to the population, you have dy dx equals ky. And this is a separable differential equation because if you just try to move your variables around, you can divide both sides by y and multiply both sides by dx and get dy over y equals k dx. And then taking the integral of both sides, you end up with the natural log of the absolute value of y equals kx plus c. So that's why we used the k earlier, because now we got a c. Luckily, because we're talking about population, the y value is always positive, so we can ignore the absolute value bars, exponentiate both sides, and we get y equals e to the kx plus c. There's a little trick here, which is that when you have addition in your exponent, you can call it e to the kx times e to the c. And e to the c is really just a constant. And so we often will just rewrite it as a new constant. We will just write it as the letter c itself. And so you will see often this just rewritten as y equals c e to the kx. This c is not the same as the old c, but they're both just constants, so it doesn't really matter. And so that would be the general solution to a population that was proportional, a population growth that was just proportional to the population. And that right there is our good old friend, the exponential curve. And it is useful for describing population up to a certain point. But then typically populations start to come back down, and that's one disadvantage of this model there. So I want to show you one more example before we call it good that is a little bit more accurate of a model, where it's not just proportional to the population itself, but it's also proportional to the share that is not the share of the population that has not been accounted for yet. So let me show you. This is a better one for showing like viral spread or something. So if we write the rate of change of the population is proportional to, let's think about like a virus, proportional to those who have it, and also proportional to the rest of the population. Okay, proportional to the rest of the population. And why is it 1 minus y? I'm letting y stand for the percent of the population here. And so this first y is the percent who has it, and the 1 minus y is the percent is susceptible. This is also separable by the same strategy as before. We go dy over y times 1 minus y equals k dx. The left side, we can use partial fractions. So we can say that 1 over y times 1 minus y equals a over y plus b over 1 minus y. getting 1 equals a times 1 minus y plus b times y. If you plug in y equals 1, you get b equals 1. And if you plug in y equals 0, you get a equals 1. And great. And so then what we have is on the left side, when we take the antiderivative of it, we get the natural log of 1 minus y times negative 1 plus the natural log of y, and that equals kx plus c. Okay. Solving this further is going to use your logarithm rules over here on the left side. So let me clear the screen. Negative natural log of 1 minus y plus natural log of y equals kx plus c. Combining these together, I get the natural log of y over 1 minus y equals kx plus c. Exponentiating, and I'm going to use the same constant trick I did before. We have y over 1 minus y equals c e to the kx. Then I want to get my y's by themselves, so I go y equals 1 minus y c e to the kx. Distribute. Y equals c e to the kx minus y c e to the kx. Gather my y's on the left side. We're almost there. And then you see the left side has a y in common. So I'm going to factor out that and divide. And so our final answer here, if I factor it out and divide, is that y equals the original right side, c e to the kx, divided by what was factored out, 1 plus c e to the kx. And the beautiful thing about that model there is that it never goes above 1, and it doesn't go below 0. And so it more accurately models the growth of a virus as it spreads to the population. So there you go. Good luck today with the activities. Please reach out with any questions and let me know if there is too much and you need some of it to be rolled forward to Friday, and I will adjust the plan. Thank you.